Hello and welcome to this 23rd set of problems on complex numbers. So, as always, I will repeat that when I am stating the problem, you should pause the video, and only if you cannot solve the problem yourself, then look at the solution. Now, without further ado, let's get started. The question 221 says that find the common roots of the equation z to the power 3 plus 2z square plus 2z plus 1 is equal to 0 and z to the power 1985 plus z to the power 100 plus 1 is equal to 0. So we are given that z cube plus 2z square plus 2z plus 1 is equal to 0. We factorize it. We find two factors, z plus 1 and z square plus z plus 1. Now if z plus 1 is 0, then z is minus 1. And from the second factor, we find z to be cube root of unity, that is omega and omega square. Now if z is minus 1, then this would become minus 1 because the power is odd. This would become even and this will remain 1, which will be not equal to 0. Sum would be 1. Which would not be equal to 0. But if we substitute z is equal to omega, this will become omega square, and z to the power 100 will become omega plus 1, which will be 0. And if z is omega square, then z to the power 1985 will become omega, z to the power 100 will become omega square plus 1, which is equal to 0. So we see that omega and omega square are the common. Question 222 says that if z1 plus z2 plus z3 is equal to alpha, z1 plus z2 omega plus z3 omega square is equal to beta, and z1 plus z2 omega square plus z3 omega is equal to gamma, plus z1 z2 z3 in terms of alpha beta gamma. Hence prove that mod alpha square plus mod beta square plus mod gamma square is equal to 3 mod z square plus mod z2 square plus mod z3 square. So we have three values, alpha beta gamma. If you add all of them, you will find that is equal to 3z1. So z1 is alpha plus beta plus gamma by 3. Now we multiply second equation. There is a typing mistake. There should be a no. Second equation with omega and third equation with omega square. Then you will find that z3 is equal to alpha plus beta gamma plus gamma omega square by 3. And similarly, if you multiply second equation with omega square and third equation with omega, you will find z2 as alpha plus beta omega square plus gamma omega by 3. Now mod alpha square is alpha alpha bar, so that will be equal to z1 plus z2 plus z3 into z1 bar plus z2 bar plus z3 bar. And similarly, mod beta square will be beta bar, which will be equal to z1 plus z2 omega plus z3 omega square into z1 plus z2 bar. Now you have to be careful here. When you take bar on omega, it becomes omega square because omega square is a complex conjugate of omega and vice versa, both way. And so the omega square will become omega. And similarly for gamma mod gamma square, we have this. Okay. Now once we have these three values, we simply add and we make all those terms 0 where 1 plus omega square comes as a factor. So this becomes 0, this becomes 0, and all these terms become 0. And we will be left with 3 into mod z1 square plus mod z2 square plus mod z3 square. Question 223 says that if n is an odd integer greater than 3 but not a multiple of 3, prove that x cubed plus x squared plus x is a factor of x plus 1 to the power n minus x to the power n minus 1. So we are given fx is equal to x plus 1 to the power n minus x to the power n minus 1. Now from the second expression, we have x to the power 3 plus x squared plus x. We take out x outside, so we have 3 roots, 0, omega and omega square. Now if we substitute f0, then it will become 1 to the power n and minus 1. This would become 0, so that is 0. 1 to the power n minus 1 would be 0. Now we substitute omega. We have got omega plus 1 minus omega to the power n minus 1. Now omega plus n we know is minus omega square, so this will become minus omega to the power 2n minus omega to the power n minus 1. Okay? So this clearly is 0. Similarly, you will find that f omega square is also 0. So clearly both of them have all common factors put together. So this would be divisible by x cubed plus x square plus x. That is what we were asked to prove. Now Another version of the previous question is n is an odd integer greater than 3 but not a multiple of 3. Prove that x plus y to the power n minus x to the power n minus y to the power n is divisible by xy into x plus y into x square plus xy plus y square. So we are given xy into x plus y into x square plus x square plus xy plus y square is equal to 0. So from the first part, that is xy, if that is 0, then x is equal to 0, y is equal to 0 are the solutions. From x plus y, we have x is equal to minus y. And from x square plus xy plus y square, we have y is equal to x omega and y is equal to x omega square. Now we start substituting them. X is equal to 0 will become 0 because this term will become y to the power n, this will be 0 and this will be y to the power n. Similarly, if y is 0, is 0. And if y is equal to minus x, then this will become 0. And this y to the power n and x to the power n will get cancelled because it's an odd number. Okay? So minus x to the power n would be negative, minus plus. Similarly, you can find that if you substitute y is equal to x omega or x omega square, the function reduces to 0. Thus, we see that it is divisible by the required expression. Question 225 says that if mod mod z1 is equal to mod z2, it should be 2, and so on up to mod zn is equal to 1. Prove that mod of z1 plus z2 up to zn is equal to 1 by z1 plus 1 by z2 plus up to 1 by zn. So in this question, we start from right hand side. We have 1 by z1 plus 1 by z2 up to 1 by zn. We write them as z1 bar by z mod z1 square plus z2 bar by mod z2 square and so on up to zn bar by mod zn square. Now we are given that the square of modulus is 1. So right hand side becomes mod of z1 bar plus z2 bar plus zn bar. So we take the conjugate over the entire expression. We get mod of z1 plus z2 plus zn bar. That would be equal to modulus of complex conjugate mod of z1 plus z2 up to zn. Thus we have left. Question 226 says that if alpha and beta are members of complex number set, so that it basically means alpha beta are complex numbers, so that mod of alpha plus square root of alpha square minus beta square plus alpha minus square root of alpha square minus beta square is equal to mod of alpha plus beta plus mod of alpha beta. So for any two complex numbers, we know that from the identities discussed in theory part, that mod of z1 plus z2 square plus mod of z1 minus z2 square is equal to 2 mod z1 square plus 2 mod z2 square. Now we let z1 as alpha plus square root of alpha square minus beta square, and z2 is equal to alpha minus square root of alpha square minus beta square. Now we have mod z1 plus mod z2 whole square. So we take that will be equal to mod z1 square plus mod z2 square plus 2 mod z1 z2. So it's now a matter of simplification, and thus you can arrive at the right hand side. So you can read this, it's a simple calculation. Question 227 says that if z1 is equal to a plus ib and z2 is equal to c plus id are complex numbers such that mod of z1 is equal to mod of z2 is equal to 1 and real part of z1 z2 bar is equal to 0, then show that the pair of complex numbers omega 1 is equal to a plus ic and omega 2 is equal to b plus id satisfy first relation, first part, that is mod of omega 1 is equal to 1, mod of omega 2 is equal to 1. Third part is real part of omega 2 bar is 0. So we are given that mod of z1 is equal to mod of z2. So this should be z2, there is a typing mistake. That means a square plus b square is equal to c square plus d square is equal to 1. Now z1 z2 bar will be ac plus bd plus I into bc minus ad. We are only interested in the real part, that is ac plus bd, which is given as 0. So ac plus bd is equal to 0 means a by d is equal to minus b by c is equal to k. So we can say that a is equal to kd and b is equal to minus kc. That means k square d square plus k square c square is equal to 1, because that will be a square plus b square. This implies that k square is 1 because c square plus d square is 1. It means k is equal to plus minus 1. Now omega 1 is square root of a square plus c square. And from this relation, we can say that it is equal to a square plus b square, which is 1. Similarly, mod of omega 2 will be b square plus d square. But we can write d square as a square from this relation. That will make 1. So these are the two parts. Now omega 1 omega 2 bar is equal to a plus ic into b minus id. Now if you look at the real part of this, that would be ab plus cd. Now if you look at a, it is ad, okay, and you look at b, it is kc, where k is plus minus 1. So whether it is plus or minus, that will be negated, and we will have ab plus cd is equal to 0. Problem 228 says that prove that mod of z1 minus z2 by 1 minus z1 bar z2 less than 1 if mod of z1 less than 1 and mod z2 less than 1. So what we do is we square this first, okay, and then we take this denominator and bring it on the right side. We have mod of z1 minus z2 square is equal less than mod of 1 minus z1 bar z2 square. Now we expand both of these because we know that mod z square is equal to z bar. So expanding this will be z1 minus z2 into z1 minus z2 bar less than 1 minus z1 bar z2 into 1 minus z1 bar z2 bar whole bar is applied on the whole. So we further simplify this. We remove the bar on the whole and apply it to individual elements. We have z1 minus z2 into z1 bar minus z2. Right hand side we have 1 minus z1 bar z2 into 1 minus z1 z2 bar. There is an extra pair of parentheses that is not needed. Now from this we have mod z1 square plus mod z2 square is greater than 1 plus mod z1 square mod z2 square. Once we have this, I'm a bit confused here because this should be less than. All right, we'll see. So okay, so this should be less than. Let me think. Right, this is z1 square and this is z2 square. This is z1 bar z2. All right, so this is z1 bar z2, which will get cancelled with this. This is z2 bar z1, which will get cancelled with this. This will be plus. Okay. All right. So this is definitely less than. This is a typing mistake. Okay. So assume that this is less than, and we have this relation. All right. Now we take z1 mod z1 square mod z2 square to the right side. Then it becomes 1 minus mod z1 square minus mod z2 square plus mod z1 square mod z2 square greater than 0. Now this makes sense because this is less than 0. This would be greater than 0. Now from this we have 1 minus mod z1 square into 1 minus mod z2 square greater than 0. Now we split this. We write it in the form of a plus b into a minus b. We have this greater than 0. Observe that mod is less than 1. So the plus part will be positive because modulus is positive. But the minus part will also be greater than 0. And hence we have proven the inequality. Question 229 says that let z1 is equal to 10 plus 6i and z2 is equal to 4 plus 6i. If z is any complex number such that argument of z minus z1 by z minus z2 is pi by 2, then prove that mod of z minus 7 minus 9i is equal to 3 square root of 2, 3 into square root of 2. So we are given that z is equal to x plus iy. So we write z minus z1 by z minus z2. It will be x minus 10 plus iy minus 6 divided by x minus 4 plus iy minus 6. Now we rationalize, that is we multiply and divide by x minus 4 into, x minus 4 minus iy minus 6. the denominator will become x minus 4 whole square plus y minus 6 whole square. And we have the numerator as computed, which we let as a plus ib. In this case, since we have to find the argument, the denominator does not matter, because when we will calculate b by I, the denominator will simply get cancelled. What we are interested in, these two parts. Now, since the argument is 1, these two parts will be equal, which is written here as x square minus 14x plus 40 plus y minus 6 whole square is equal to 6 into y minus 6. Gives us x square plus y square minus 14x minus 18y plus 112 is equal to 0, which is equal to mod of z minus 7 minus 9i square is equal to 18. Now 18 is nothing but 3 into square root of 2 squared, and thus we have proven the required equation. Question 230 says that find all complex numbers z such that argument 3z minus 6 minus 3i by 2z minus 8 minus 6i is equal to pi by 4 and z minus 3 plus I is equal to 3. So this is nothing but a similar question as the previous one. We have z is equal to x plus iy, and we write the given expression, we rationalize, we let it as a plus ib. Now a plus ib argument would be 1 because it is pi by 4, and pi by 4 is 1. So the denominator will get cancelled when we write b by a, and it will be imaginary part by real part, both will be equal. So we have the equation 6 square plus 6y square minus 36 minus 24y plus 66 is equal to 12x minus 12y minus 12. So divide the entire thing by 6, you get x square plus y square minus 8x minus 2y plus 13 is equal to 0. Now we are also given that mod of z minus 3 plus I is equal to 3, which essentially means x is equal to minus 2y by 6. So we substitute this over here, we get 5y square minus 10y plus 1 is equal to 0. That means y is equal to 1 plus minus 2 by square root of 5, and x is equal to 4 minus plus 4 by square root of 5. Once we have found x and y, we have our z. So with this, we come to the end of 23rd set of problems on complex numbers. There are a lot of problems still left. I hope that you have found this video useful and informative. So as always, the same thing has to be repeated, that subscribe the channel, like the video, and if you have to say something, then please use the comment feature of YouTube. It's simple. Why I say this is because I want some sort of motivation, because if nothing happens, you don't feel motivated. You need sort of a reward when you take an effort. And those likes and subscriptions motivate you to do. And the second thing which happens is the reach increases. I want these videos to reach as many people as possible so that they also get the benefit. And yeah, do let me know in comments what you think about the video, or you can talk about other stuff, whichever you want. Thanks a lot for watching. Have a nice day.